Thank you. Thanks, ladies and gentlemen, and thanks for giving me this opportunity to introduce the power electronic solutions for hybrid electric vehicles and renewable energy. And actually, every time when I talk about power electronics, I will be pretty excited. Not only because this is an interdisciplinary research involved so much courses inside, so much knowledge inside, but also because every time when I think of so much things to learn, that will make me excited. For example, one night when I was killing my time in front of the computer, sipping the red wine, watching the scary movie. One of my students in the lab texted me, Kevin, I'd like to stay late tonight to work on the 10 kilowatt PFC, power factor correction. I want to reach the 97% efficiency. Would you join me? I said, yes, definitely. So I just joined him at 10 o'clock, then we finished. We wrap up all the tests in the midnight. Then I lost my sleep. And next morning, I feel pretty grouchy, and my student said, sorry, I should not let you go. I said, no, I really wish all my students will text me or email me all the report and experiments in the midnight or at the weekend. So that means you are working. Yeah. So eventually, right now, all my students do so to wake me up in the midnight. This is the first thing I need to mention. Secondly, I should say, for the power electronics solution, for the power electronics, yes, I have gained my bachelor degree 10 years ago. I have been in this domain for more than 10 years. But I'm only coming here today to give a talk, not a speech. Because for the speech, it's the job of the experts with specific knowledge, with profound knowledge in some domain. I have been in this domain for 10 years, but it's still hard to say I'm the expert. I'm still has a long way to go to be named as expert. So today, if I look back at the past 10 years, I should say I experienced a lot. I learned a lot of lessons. But sadly, again, not too much wisdom in this process until I joined the ECE, Catherine University, organized a team, a strong team to help me gain the wisdom. So today I'm going to share something, if it could be called as wisdom with you. So first, I'd like to talk about some research activities in advanced power electronics lab. And then why power electronics, what is power electronics? Just to generalize this domain. And specifically, I'm going to talk about power electronics solutions for PHEV, plug-in hybrid electric vehicle, and renewable energies. And then say what kind of opportunities and the challenges in this domain. Eventually, at the end, I would like to discuss a bit educational, industrial, and research preparation that we should do. I joined Catherine in July 2010, and after 1 year, I feel pretty lucky that with the help of our department, we will be able to establish an advanced power electronics laboratory. Our research scope includes motor drive system, battery charger, vehicle electrification, semiconductor switches, battery management system, battery packaging. Anyway, anything associated with power electronics. And in the past 11 months, we received 5 company contracts over $500,000 to do a lot of research. And in this process, we created 8 positions, 4 as campus co-op. So basically, in the power electronics, when I taught power electronics, I saw, okay, there's a lot of genius people who are interested in this domain. So I would like to ask them to join my team to do some specific projects. And also, we have some research scientists, 4 research scientists, research scholars, and 1 postdoc joining our team to meet the requirements and needs of automotive industry. And we also well published in this domain. We published some journal paper and some books and conference paper. Here I should say what? Hall of the Fame, right? Yeah. So basically, we have battery charger group, several people working on the battery charger. We have a motor drive group working on the 50 kilowatt motor drive traction motor for the PHEV. And we also have some group working on the battery management system and semiconductor devices. So I just want to point to this guy, Nelson Wang. He just came over, after consecutively working in the lab for 3 terms, he just came over on the Monday to say, hey, professor, I got accepted by MIT for the graduate program, which just make my day. And I say, okay, all the help you paid really paid off. Okay, really pay back. And specifically, we have research activities. We help Sino EV, a company located in Silicon Valley, to develop a 50 kilowatt traction inverter for the electric vehicles. We helped the Tenneco to design a 12 volts, 1 kilowatt motor drive system. And we delivered 2 products for Magna e-car. One is 97% efficiency power factor correction, 11 kilowatt. And we delivered another 10 kilowatt battery charger for Magna e-car 2. And we also helped Progressive Dynamic, is a local company, battery company, to benchmark a lot of battery chargers to say what's the impact of the charging algorithms on the battery lifetime. Right now, we are kicking off the proposal with Chrysler company to help them design some DC-DC converter to link the high voltage battery, lithium-ion battery, with the 12 volts lead-acid battery to transfer the energy. Therefore, we will realize the electronics alternator in PHEV. But these parts are only the motor drive system and the EV chargers. In addition to that, we have our own interests. We want to diverse our research activities. Do not place all the bags in one basket, right? So in this case, we have the wireless charging system, we have the battery research, and also the solar energy. Let's see whether I can. Okay, good. So specifically, if you look at what's happening for the PHEV, for a series PHEV, what's our scope? The dashed square is our scope. We care about the generator, we care about the inverter, and the DC-DC converter. And also, we care about how to link the grid with the battery, the high voltage batteries in the PHEV, and how to use the energy stored in the high voltage battery to drive the motor. So what's the power electronics, and why power electronics? I guess the students in my class know what power electronics is. Still, in the different textbooks, we have the different concepts. We have the different definition for power electronics. We know power electronics is a branch of engineering that combines the energy generation, energy transformation, and distribution of the electricity through the electronics means. It contains the information and energy. But still, these definitions look so dry. It's vague for you to understand. So I'm going to show you some research activities in the video to help you understand what power electronics devices and the system really look like. So first one from Alan Taylor, our research scientist.
Alan Taylor. I'm a recent graduate of Kettering University working as an engineer in the Advanced Power Electronics Lab. And this is a 10 kilowatt power factor correction module. Most electric vehicles found on the market today require a large amount of energy storage to meet the distance driving demands of everyday vehicles. And so one downfall of such large energy demands is charging that large energy storage device, battery. So with this device, we can realize a high charging speed due to the high output power capability of this circuit, and also realize a high efficiency due to the semiconductor devices and control algorithms used. This device takes in 3-phase, 120 hertz AC voltage and current, and passes it through a 3-phase rectifier bridge to generate 400 volts DC output at 10,000 watts with 97% efficiency.
I should say, after I joined Kettering, I encountered a lot of good luck. Alan is one of my good luck. He helped me design everything pretty arty that I do not want to damage. I even do not want to try by myself. I say, you try by yourself. Okay. And second one, coming from our campus co-op. One of my my best student in the power electronics class.
So what we have here today is a 1 kilowatt power conversion system. The system is designed to take a 12-volt source, like a car battery, and change it to a 300-volt source that powers a three-phase motor that you can see here. So again, taking the 12 volts and feeding it into a DC-DC converter, switching pipe that boosts up to 300 volts and feeds each leg of the inverter to the motor. The motor is designed to run a clean air burning system for a diesel vehicle, used in the diesel particulate filter to help reduce particulate emissions.
This is a motor drive system, and this is all the products associated, a pre-product associated with a PHEV or conventional vehicle. And next one. From Mori Yatsu, the Presidential Award, Gold Award, and Outstanding Thesis.
Hello, I'm Mori W. Yatsui at Kettering University. Hello, I'm Mori W. Yatsui at Kettering University's Electrical and Computer Engineering Department, and I am working with SOC estimation with lithium-ion batteries using open circuit voltage, Coulomb counting, and Kalman filter methods in order to obtain an estimated SOC. Here is a National Instruments software that I have run or developed to create pulse charging estimation for open circuit voltage, constant current, and Kalman filter SOCs. And here is a National Instruments MIDAC that is measuring the volt terminal voltage of a battery and is also running a current transducer, which is measuring the current coming out of the battery, along with a NFET transistor, which is turning on a relay, which determines whether or not a load or a charge is attached.
He and I both, we authored one paper in Vehicle Power and Propulsion Conference in 2011 in Chicago. And after he presented, a lot of university professors came over to say, shoot me 2 questions. The first question is, where is Catherine? So, which make me frustrated. Then, the second question, it was, is he really a senior student? Looks like what he did is a master's thesis. And I say, yes, this is Catherine. And the last one, our independent study.
University EC Department Advanced Power Electronics Lab. Today we're going to demonstrate to you our wireless power transfer system. And if you look over here, we have the strongly coupled coils. The power will be transferred from the primary side to the secondary side. And here we have our PFC board. This board will generate a PWM waveforms for the coil. And today we're going to let up this bulb. We're going to reach about 120 watts, but we can go much higher than that. So just for the purpose of demonstration. Alright, let's start the PFC first. Reset. When the orange LED lights up, it's working. Okay, now let's start our power supply. Let's give some power. And if you look over the bulb, it will start lighting up. And we keep increasing. We got more. Now we have about, let's see, 140 watts. So it's working very well. And thank you very much.
The air gap was about 20 to 30 centimeter. And so eventually, if we make it make it better, then we could charge the battery in your vehicle wirelessly. So I forwarded this video to to some of my friends in different universities, and the feedback is, now all my department is watching this video. So let's take a look. Okay, now you know what power electronics really look like, right? What power electronics could do. So let's generalize a bit. This is a picture in my mind that the future world we should live with. Not we should live, we might live with. So If in the future we could use renewable energy, let's say the wind energy and the solar energy, transfer this, change this non-stable energy to the stabilized energy, then feed it to the motor drive system or to the grid for the vehicle to charge, then we are going to create a very environmentally friendly community, correct? So some of the students come over to ask me, I'm into the renewable energy, so what I'm supposed to do? And my answer is first that you need to know the material. You need to know some solar. You need to know how the wind energy works. And secondly, you need to know power electronics. Because power electronics in this area, in this domain, is the critical linkage between the non-stable energy to the stable energy. And think about this way. Several years later, you are going to drive an electric vehicle. Then when you drive the electric vehicle, you might want to charge your vehicle. Therefore, you need to transfer the AC energy to the DC energy, which your battery could accept, right? So that needs the energy transformation, which is a job of power electronics. And sometimes in the peak time, you want to sell the battery energy back to the grid to earn some money, right? So in this case, that still need the power electronics to transfer the DC energy in your battery back to the grid to transform it into the AC energy. So let's look at what DOE said. DOE said with the next 2 decades, nearly 80% of the US electricity will go through the power electronics. That's a good news for us. That means a lot of job opportunities we are going to create. And through the power electronics, we could save the energy. That's one of the major jobs that power electronics need to reach. And since power electronics will modify the form of the electrical energy, therefore this domain expects to see a lot of innovations. For example, a solid-state lighting, LED lighting system, intelligent motor, electric vehicles, and smart grid. We have been talking smart grid for many years, right? For more than 10 years. And power electronics make it feasible, make it realizable. Let's take a look at one case. That's a system. This is a system I designed 5 years ago. It's a 6,000 watts, 1.25 megawatt motor drive system. So what's this monster for? This device is for us to drive a huge motor to realize the water pumping, to realize the steering. So for example, here is me. For 5 years ago, and my friends always say, "Oh, is this you?" I say, "Yes," and they say, "Oh, you are old." I say, I will say thank you because I have been tormented by power electronics for many years. And this motor is about my height, so you could imagine how big this system is. Then what's this system for? This system is to drive the motor at a different speed. With a conventional way, how are we supposed to change the speed of the motor? We are going to series some resistors on the rotor side to decrease the speed of the motor, which turns into that you are going to waste a lot of energy on the resistor side. But with designing the power electronics devices with 98% efficiency, we are going to change the speed as we want, change the motor speeds as we want. We could definitely first convert the AC energy to the DC. Then use this DC, invert this DC energy back to the AC. Well, this AC frequency is changed by us. So in this case, we don't have any energy loss in the process. So look at here. This is a wastewater tank. So industry will generate a lot of wastewater. So this wastewater sometimes has a high level, therefore it requires your motor run it faster to dispose this water. Sometimes this water level is low, therefore you do not need to run your motor at the rated speed. So how to adjust the speed of the motor drive system is our job. Renewable energy. For renewable energy, definitely, solar panel only generates the DC energy. So how are you supposed to sell this DC energy back to the AC, right? That's the job of a DC-AC inverter, the power electronics inverter. Meanwhile, think about this way. Your solar energy is forever changing with the solar intensity. Therefore, the energy generated by the power generated by the solar panel is not stable at all. So you cannot directly hook up this solar panel to the grid. That will create the trouble to the grid. So basically, power electronics becomes like a buffer between this non-stable energy source to the stable energy source. And eventually, as I said, if everyone will place the solar on your house roof to charge your vehicle, you are going to create a self-sustained community, right? So you could totally get rid of the grid. Oh, definitely, at that time, grid will not be happy. Right? And another biggest domain of power electronics is power supply. So one of the typical example of power supply is battery charger. So what we designed for Magna e-car is one devices first convert the AC to DC. The other devices convert the DC to the energy that your battery could accept. So if we form these two parts together, you are going to have a complete battery charger, which accepts the AC energy and accept the AC energy to charge the battery. So where we are, we have three different levels. We have three different types of battery charger. Some of the residential battery charger requires you more than 8 hours to finish the charging. Some of the charger for the workspace requires you 2 or more than 2 hours to finish charging. We are on the top of this pyramid. We could finish the charging of the PHEV within 1 hour. So that's a fast charger. And in this process, our efficiency is pretty high. Therefore, in the charging process, you won't lose too much energy. And now, with the technical preparation of motor drive system and the battery charger, we could go ahead to talk about the electric vehicle. Power electronics make electric vehicle and the PHEV possible. Here are some figures to show you. We have a lot of population who drive some appropriate range every day to use the PHEV. Therefore, PHEV is important for us. And also, it can realize it has an excellent economic performance. For example, every day, if you only drive 11 to 15 miles, then the monthly gasoline fee will be only less than $20. So this is amazing, right? But that's actually not the ultimate goal of PHEV. The ultimate goal of PHEV is you could use the electricity from the grid. While the electricity from the grid could come from the diverse energy resources. The ultimate goal for the PHEV is to get rid of the dependence of fossil energy. Think about this way. If renewable energy could be used to transform the renewable energy to the electricity, use this electricity to charge your vehicle, then this society will be totally green without any emission, correct? Without any pollution. So that's our ultimate goal. So power electronics make renewable energy application possible, make the charging of the electric vehicle possible. So that's the critical position that the power electronics are located. So in a summary, what power electronics could do: energy saving, energy storage, energy transformation, energy transfer, and energy harvesting. So everything is about power and energy. So power electronics is important, correct? Power electronics is interdisciplinary, means you have to know everything, right? So my students come over to say, Kevin, what I should know to learn the power electronics? I say, if you want to pass my course, you probably know, you need to know microelectronics 1, you need to know the circuit 1. If you want to be a qualified power electronics engineer, you need to know everything. Yeah. Then power electronics is interesting, correct? So power electronics has a lot of opportunities, but unfortunately, a lot of challenges. So let's go through. First, power electronics creates the job opportunities. One of the popular area is vehicle electrification. When companies come to my lab, the most frequently asked question is, where are those guys supposed to go after this lab? Are they going to shoot us the resume to me? And I say, well, it depends. So a lot of companies right now putting a lot of effort to electrify the vehicle. They need the power electronics expertise. Secondly, in the remote areas that the electricity cannot reach, we need the solar-based water pumping and the lighting system. So in the daytime, you could use your solar to pump the water, and at the nighttime, you could use the excessive energy stored in the local battery to light your community and light your house. So that gives the opportunity for the renewable energy. And look at this figure. 40% of our motor is pumps, which need to adjust the speed. 30% of our motor is fans, which need to adjust the speed too. But how many really use power electronics? Only 3%. That means we still have a long way to go. That's exactly what ABB and Siemens are right now doing. They are doing, ABB and Siemens design the motor drive system, the medium voltage and high voltage motor drive system to drive the motors to drag the pump, the water pumps and the fans to adjust them in the speed, to adjust their speed. And meanwhile, in addition to the industrial opportunities, power electronics will give us a lot of research opportunities. So let's take a look at what DOE sponsored. DOE sponsored power electronics in a lot of different directions. One of the major directions, if you take a look at what they sponsored these universities and the companies, they care about the new material. Eventually, for the electrical engineering, if we do more and more electrical engineering, we will find out the most critical point is material. So that means in power electronics, we always need the high efficiency and high frequency system, which can only be realized by the excellent material-based power electronics devices. So we say one generation of semiconductor technology determines one generation of control. Without this semiconductor technologies, we cannot make it. And meanwhile, the control strategies will push the development of the semiconductor technologies. So we say the material, the semiconductor technology, and the control algorithms, the control strategies are actually the twins. They push each other to develop. For example, when Magna launched the call for proposal for me to say you need to design a 97% efficiency power factor correction, I said I have no chance. I have no chance to realize it, but I cannot tell them. so I come back and say, okay, what kind of solution I can find? So I cannot do it. That's a conclusion based on the 4 years ago. 4 years ago, I definitely cannot do it. But right now, Infineon and other Infineon and Semicon, these major semiconductor companies actually kick off a lot of more excellent switches, which we could do it. So with using this kind of switches, with using this kind of semiconductor switches, we could definitely reach the higher and higher efficiency, and meanwhile shrink the size of our system. So that's something we can realize. This is the results this is the efficiency we could reach 4 years ago. And that's the efficiency we could reach right now with the most excellent switching. So how much we could increase? More than 3%, right? So I should say, right now we are living in a very best time. In the best time, that we have a lot of choices to choose. We have a lot of excellent material-based semiconductor switches to utilize. But I should also say we are living in a worse time because of too many choices. You will get amazed by what's going to happen. And definitely, in this process, we also need these devices could undertake the high temperature because we are going to put it in the vehicle. So without taking the high temperature, we have no chance to make the product. And fortunately, these devices could undertake the high temperature. Another case I want to share with you is the 10 kilowatt fast electric charger. 4 years ago, we cannot make it because there was no high voltage, high current devices in this domain yet. So right now, 4 years later, we're happy to find out that the switches are ready for us. So we could go ahead to use it to realize some goals we cannot think of 4 years ago. So that's some results I want to share with you. What Magna want to do is they want to realize the high efficiency, 97% efficiency, which we reached at the low voltage. But they also want to reach 92% efficiency at 8 kilowatt. Ultimately, eventually, we give them 95% efficiency. That means we give them 3% again, so which makes them happy. Let's take a look at the second branch that DOE sponsored. The second direction DOE sponsored is, look at here, Georgia Tech and MIT and other Virginia Tech. They care about, I gave you the switches, I gave you the control algorithm. How are you supposed to integrate the system together? Make the system design compact and make the system has a higher and higher power density. So that's called the system integration. And particularly, government invest millions and billions of money to develop the power electronics expertise centers in a lot of big universities. For most of these expertise centers, what they are doing right now is renewable energy and vehicle electrification. That's the two major directions of power electronics. And definitely compared to them, we still have a long way to go. What we have been doing is integrating all the components on the limited area and try to make the system reliable, pretty ready for the market. But I should say, we are still in the beginning. We are still not reaching our ultimate goal yet. We have a long way to go. And another challenge that power electronics gave us, if you are in this domain for some period, you will find this domain needs a lot of experience. But meanwhile, it is driven by the policy, heavily driven by the policy, and also heavily driven by the market. If you travel the world, travel from Europe to Asia, especially China and Japan, and then travel to US, you will find out the design methodology of power electronics in those countries are a bit different, are totally different. For example, what happened in China right now is everyone is doing the vehicle electrification simply because government wants to do so. The government say, okay, we need this part. We will do it whatever we will cost. So everyone will go ahead to do it. So this is why I cannot find another postdoc coming here, because he wants to say, he actually said, oh, I want to open a company to design the PHEV by myself. Okay, go ahead. And so if you look at, for example, another case is wireless charger. Wireless charging system has already reached the productivity in Britain, in most of the European countries. But in China, in Japan, it's hard to say. We don't know whether it has a future or not. Because this kind of products could be regarded as a luxury. That means you do not want to plug in. You just want to get out of your vehicles and leave it charged alone. While in China, in Japan, they don't have the garage. We only have the what? They only have the apartment. So where is this one supposed to place, right? So that's another challenge that the power electronics gave us. Design of the power electronics system is important, but we need to follow the policy, the government policy forever. We need to follow the market forever. So the fourth challenge that power electronics gave us is a lot of issues to learn. You need to learn the motor. You need to learn the digital signal. So we have too much things to choose. We have too much things to learn. Sometimes we even need to know the mechanical design because we need to dissipate the heat of the switches. So therefore, we need the heat sink. How to place the heat sink is a critical issue. And pay attention. This is a no productivity, no future domain. So we have to, when we do the research, we wish our students and our people in the lab will gain a lot of experience. We will do a lot of hands-on projects. These hands-on projects is not for fun. This is for serious issues. This is also why companies find that education of power electronics and the training of power electronics has a huge gap. Meaning, we can provide some power electronics expertise to the company. However, this kind of expertise is not what they want. Right? We can teach the student how the buck converter, how the boost converter, how the power electronics inverter working. However, company need you to design this inverter, which is totally different from our textbook. Therefore, we have some gap here. We just hope that our lab or the similar lab could fill this hope to bridge the academia with the real industry. So this world forever has a lot of problems, new problems emerging. So power electronics need to fix this problem. Only one Toyota Prius burned their battery. We began to think of how to balance the battery. Therefore, power electronics go to the battery management system. Only one, the battery state of the charge is hard to predict. Therefore, you damage the battery, then power electronics help to predict the battery. So we use the extended Kalman filter to to get the state of the charge information, to predict the state of the charge accurately. Therefore, your system, your battery in the vehicle will be safe. And only when we charge the battery with some algorithms, we damage the battery, then we will need to say what's the best charging algorithms for the battery. Therefore, power electronics people will be busy again. We need to figure out what kind of impact that the battery charger will have for the battery stacks. So in overall, we have a lot of research activities in power electronics. Fundamental research activities, we need to know the material. From the applied research activities, we need to know the PHEV, fuel cell renewable energy. And also, this is, as I said, this is an interdisciplinary domain. Therefore, we need to know a lot of other stuff, let's say the thermal, packaging, material, and even communication. So, as I claimed again, this is the best time, this is the worst time. And in this process, just since I gained some experience, maybe not the wisdom. So what I'm thinking is maybe we need to think of something general. How are we supposed to prepare for the power electronics application? Definitely, first one will be widely interested and keep learning. That's the most important thing. Secondly, microscopic and macroscopic. We need to know the control algorithms. But meanwhile, we need to know the semiconductor behaviors. So that's different time scales. We need to be software and hardware prepared. I hope this one will not discourage you to learn the power electronics. Okay, I hope just to say this one probably will give some beneficial points for us, and be innovative and realistic. Meaning think globally to say what's happening in this world. But when we have to design something, we need to deliver it. That's what we need to be realistic. Okay. And pursuing and persistent. I always talk to my team. In power electronics, we don't have the gray area. We have a white area, we have the black area, but we don't have the gray area. Meaning, what you achieved eventually will be either 0 or 1, either failure or success. There's no middle area, to say quasi area. So what APEL could do, that's what I'm thinking. We could definitely go ahead to reach the productivity with a lot of companies. That's what we concern right now. And we could also think of identifying the evolutionary and revolutionary topologies, and also meanwhile to expand our research activities from the vehicle electrification to other domains. Electrification is important. Vehicle electrification is important. But right now, the future is hard to see. It's slowly growing, but when it will reach the final marketability is out of our scope. So I'd like to acknowledge everyone who support us, all our APEL members. Without you, we cannot make it. And the support of our ECE and support of Catherine. Any question? Thank you. So I guess this question is about how are we supposed to transfer the energy from the two coils, right? So what we use is called the resonant. So if you take a look at the paper published in Science in 2007, what MIT people has been doing is to use a parasitic capacitance between the coil and the coil to resonate with the self-inductance. Think about this way. If you have two objectives with the same resonant frequency, and also they happen to run at the same frequency, then what's going to happen is the receiver will receive the energy from the source without any problem. Just like when some opera singers are singing the songs and the frequency of her voice it happens to be equal to some glasses full of the wines, then the glasses will explode, right? So what MIT people has been doing is make sure they have the same wire, same coil has the same frequency, and meanwhile they will launch the energy with the same frequency. So, but the problem for that design is the parasitic capacitance is pretty small. Therefore, the frequency is very high, 10 megahertz. From the semiconductor point of view, we have no chance right now to deliver any energy above 10 megahertz in the power electronics way. Therefore, the lab doing right now is to try to push this frequency as low as possible. So in this case, for a wireless charger, we have no way to shield it, right? So if you generate too much noise, then what's going to happen is your radio will receive this noise. Your vehicle cannot run. Therefore, we have to make sure your system frequency as low as possible, not interfere other components in your vehicle.
Thank you.
Thank you. So this question is about maybe the electric vehicle will create some healthy problem to the human beings. Well, first I should say I have been away from China for 4 years, so I really don't know what's happening there. Okay, and secondly, I believe electric vehicle involved a lot of power electronics components inside, which could create the different noise to the human bodies. That's definitely what we need focus in the future. But right now, I didn't say this kind of report yet. And I believe, as I said, ultimate goal for the PHEV to create the zero emission. But definitely it will create some side effect, I believe. For example, like renewable energy. Right? Think about the solar energy. Everyone says solar energy will create no emission. But think about when you create the PV panels. Right? In this process, this is a huge pollution. This is why most of the PV panels right now were made in China. Okay. And secondly, think about this way, even the wind energy. Wind energy needs a lot of places. So wind energy, if you want to build the wind energy factory, therefore what you need to do is occupy a huge place. So it will create the environmental side effect too. And also, I read some report that with wind energy applied, some birds even do not come here because it changes the wind direction. So definitely, I should say everything is kind of like every design of power electronics is a trade-off, and everything is about a two-edged sword. It has a best side, it has worst side. It only depends on how are we supposed to utilize it. You know? So I guess this question is about how power electronics are going to assist the development of a smart grid to use in the house, right? So if you look at the figure, well, again, this is only my personal opinion. This is my idea how the smart grid should work. So the smart grid could use renewable energy to realize a grid-tied system to sustain your house. If someday your grid totally devastated, totally black out, then what you are going to do is use the energy stored in the local battery, which was charged by the PV to charge your vehicle and charge your house. So that's a simple one. And meanwhile, in this case, the smart grid, another critical point for the smart grid is communication. So the householder need to know how the battery works, how much energy you need to consume from the battery, and how much energy you really saved. And meanwhile, since you get rid of the grid, then grid will ask you to provide the specific energy for them to monitor, to control. You definitely do not want to play anything inside yourself without letting grid know. For example, what's going to happen if your devices, your power electronic system failed in this process? Then you are going to give the grid trouble, right? So right now, another research domain is called the power line communication. So we are going to use the line, the electricity line. Right now, only carry the power. But eventually, we want this line also behave as a communication line, which could communicate between your house, communicate the house with the electric grid. So definitely, in this process, one of the obstacles is, for example, we designed the motor drive system to tie it with the grid, but the grid feel reluctant to use these issues because the reliability will be the first concern. Think about this way: if your system failed, you create the trouble to the grid, then maybe it will create the whole community that was blackouts, right? So, as I claimed here, primary concern is reliability. Cost and reliability are always the most important concerns in the power electronics.